streaming. Nice. All right. So we are pretty much done with floating point numbers, although we have projects to do. As far as discussion is concerned, I'm going to call it done for now. And it is not a part of exam 1. Okay, I know I've been a little bit confusing, okay, but I was corrected by one of your classmates and say that, nope, earlier, I said it would not be in the test, so it is not going to be in the test on Thursday. Is that okay?
Why is it going to be on the test Thursday?
Floating point numbers, double. Not on exam 1. So it will be on exam 2. All right, so let's see. I think we can move on and talk about D flip-flops and the von Neumann architecture. So we are now moving on to, from number representation, we are now moving on to von Neumann architecture and also the memory device. Because that is actually what makes the von Neumann machine possible, is the ability to remember things, okay? All righty. So are we ready? Okay. So who has checked out this guy, von Neumann? No, nobody cares. Okay. So if you guys don't care, I do. See, if all of you say, yeah, we know who he is, and these are the things that he has done, then I would have no interest to talk about him at all. It's the reverse psychology thing, right? So his name is John von Neumann. And apparently, my Deutsch is not very good, and I was corrected multiple times of how to pronounce his last name. So it's not von Neumann, it is von Neumann. Does anyone speak German? No? Okay. I suppose you can click on that pronunciation thing and see if it works. Von Neumann. And he's Hungarian, okay, but the name is close enough. Okay, so this is the guy, and he is kind of in some way similar to Alan Turing in terms of contribution to computer science. Yes?
Did you already make a recording?
Yes. And I can double check that too. So it's good to double check. It takes about a few seconds to double check, but it saves a lot of trouble down the line. Okay, so we are recording indeed. So this guy is kind of like in some way he's like Alan Turing, but in many other ways he's opposite to Alan Turing. So if you look at his birth and his death, he's only about 50 something when he passed away, and that's pretty early. I mean, the guy passed away, kind of before his time. So from that perspective, he's kind of like Alan Turing, where they both kind of died early. When you look at his contribution, it is also very significant. Alan Turing contributed a lot to the theoretical side of computer science. What is theoretically possible, what is theoretically impossible, regardless of what you use as a computer. Okay, whether you use relays, mechanical components, electrical components, or whatnot, optical components, it doesn't matter, because the pure theoretical side of computer science describes any computational machinery and not just electronic computers. But his contribution is also very important, because before him, the only way for you to reprogram a quote-unquote computer is to rewire the actual wiring connecting the components of a computer. Okay? So you can probably imagine there's no such thing as downloading an app. Okay? What you do is you make a copy of the new schematic of how you're supposed to rewire everything. You open up the computer, or in your case, your phone, okay? And you look at all the microscopic wiring, actual physical wiring between the components, and then you start to change those things. And that's how you, quote unquote, reprogram a computer before him. Okay? So his contribution to computer science is the introduction of the concept of, hey, maybe we can have the computer's memory in addition to remembering numbers and data to process. In addition to that, we can also use the memory of a computer to remember instructions. So now we can use memory for two purposes. One is to remember what kind of data we are processing, the intermediate results and stuff like that. But the other one is to remember what am I supposed to do with these numbers. So instead of hardwiring what a computer is supposed to do, it is now quote-unquote software. Is that making any sense? So without him, there's a lot of stuff would not have been possible, or I mean, just think about updating the apps of your phone. You'll be reconnecting millions and millions and millions of tiny little wires. It's not going to happen. So from the practical standpoint, von Neumann actually has nearly as much as contribution as Alan Turing. Without von Neumann, we would still be using computers that has wires in the back, and you have to change the wiring to change programs. So do we have any questions about his contribution and why it is significant? Yep.
You said the computer would remember itself. It would remember what? It would remember like how to connect to make the new program, or what would it remember?
It will remember instructions. So that is a topic that is kind of long, and that is going to lead us to the processor that we're going to talk about. Okay, is how do we use memory to remember quote-unquote instructions, and how do we get an instruction and understand what to do with it. So before him, there's no really such thing as a central processor, because it's just wiring across all the components, and it's really much more difficult to specify sequences of instructions because everything depends on hard wiring. All right, so this guy is also he also has other contributions in addition to computer science. So when you look at what fields he's really good at, it's a long list, right? I mean, this is a pretty long list. Everything from mathematics to physics to quantum, statistical mechanics, economics, computing, linear programming, self-replicating machines, stochastic computing, and statistics. Now, you might say, well, I can take all of those classes too, but he is considered by geniuses or genii of each of these fields as the genius of that field. So that makes him kind of special, right? And one of the things that he did was the invention or the implementation of the hydrogen bomb. And people think that that's what actually got him. What killed him was cancer. And he got cancer. Most people think he got it because of the radiation exposure when he was testing the hydrogen bombs. He also coincided with Albert Einstein. They belong to the same time frame, and they both taught at Princeton University at about the same time as well. Now Einstein is a very classical INTP, okay, introverted person. So as an INTP, Einstein would like to work on his stuff alone and not getting disturbed and stuff like that. This guy likes to listen to polka music loudly in his office when he works. So down the hallway is Einstein, who's always complaining about that music.
So they weren't friends?
I don't know. I would assume that when the music is going on there, they were not friends. When the music is out, maybe. So interesting guy. If you want to read up on his contribution, it's actually quite amazing. What this guy can think of. Okay, so that's him. And just kind of put a face to the term, von Neumann, because every single computer, almost every single computer that we use today, is a von Neumann architecture. So it's all because of him. All right. So the first thing, there are very few links here because a lot of this stuff is kind of interactive. I kind of have to teach it in a way that is, I can use LogicSim to teach many of these concepts, but not very easy to teach these concepts otherwise. So the first link is this one, a D flip-flop and other memory devices. And if you had a chance to read this ahead of the class, I think that would be really helpful because this is the first time we actually see a memory device, And the first one we're going to see is not a D flip-flop. It is called an SR latch. And it is one of the most basic memory devices. You can look at it as individual gates, okay? And what makes this unique is this type of circuitry has quote-unquote a feedback. The output of some of the gates goes back to the input of some of the other gates. So it forms quote-unquote a loop, okay? But it's not exactly a loop the way we understand in programming because it's not structured like structured loops. So what we'll do is we'll take a look at the circuitry description, okay? And by the way, this is just me borrowing C and C++ programming. So NAND2 with that uppercase N is describing quote-unquote the class of NAND2. Input pin is once again the name of the class. Output pin is the name of the class. The lowercase stuff like N1, N2, SR, Q, and NQ, those are your objects. Those are your variables. Okay, so I'm instantiating variables. The circuit, you can kind of look at it as a global object to represent the actual circuit that we're constructing. And an add node is adding a connection. And a connection is basically connecting different ports of different components together. So I'm just converting the way we draw stuff in Logisim into a way that we can describe it in just programming method. Is that okay? Is this notation doing okay so far? Okay. So we're going to go through this line by line and figure out what this device would look like if we were to draw that out using Logisim, which we will do in this class as well. So the first node is connecting the pin of S to N0. This means the first input of N1. So what we're really doing is we are connecting the port of input pin S to the first input of N1, which is a NAND2 gate. Okay? And then the second line is going to connect R, which is another input pin, to the other input of N2, which is not N1. The third line is connecting the output pin of N1 to the input pin, to one of the input pins of N2, but also to the output pin Q. And then the last line is connecting the output of N2 to the second input of N1, but also NQ as an output pin. All right. So I'm pretty sure most people cannot visualize all of this. I mean, if I didn't draw this out, I would not be able to visualize it as well. So the first thing we want to do is to visualize and take a look at this circuit in Logisim. Yep.
On the last line for N1.u, is that a dot or a comma?
It should be a dot. Okay. Yep. Now this type of description is kind of foreign to this class because we have not really talked about a hardware description language, HDL, in this class, and we're not going to use this format much after this particular module. But in your other classes, okay, if you transfer to a 4-year university and you are in the computer engineering department, or you're in the CSEE type of department or EECS department, you most likely will have to design a much bigger processor, much more complicated, and with a much more complicated processor, using Logisim is not going to be a very good idea. Because anything that's graphical, like Logisim, means if you need to make any changes, you have to move things out of the way so that you have room to put new components in, and it's really, really messy. This is a lot cleaner. I know it's not very visual, but it's a lot cleaner. And you can also use loops to instantiate things, like stamp out things and specify how things are connected. So that is the general idea of HDLs, hardware description languages. Okay? There are two main HDLs. One is called VHDL, and the other one is called Verilog. So those two are quote-unquote industry standards. Verilog particularly is the industry standard. Yes, question?
Verilog.
Huh?
Verilog.
Verilog. Veri. V-E-R-I-L-O-G. The veri part comes from verification. So that particular language was initially only used to do validation of circuitry, but it was later on also to describe hardware. So for those who are interested, I can show you the links to this. So the first one is Verilog, and it's a Verilog is not a very well-defined programming language. It's kind of like C, has a lot of kludges. It's not really the best language, but it is very practical. A lot of people use it. The other one is called VHDL, which is kind of more like Ada in terms of the programming languages. So this one was designed, much better in a much better way, but it's less used in industry because there are fewer implementations of VHDL. But they are basically, if you look at the code of Verilog, it looks like a C program. It has got loops, it has got conditional statements and whatnot, but instead of specifying what to do, the program itself, it's actually, look at it as PHP. Okay, PHP is typically used to generate HTML documents, right? These languages are used to generate schematics, the description of the actual gates, how you connect various components in a computer. Okay, so it's fun stuff. It's just that it's not the focus of this class. All right, so getting back to our notes here. Okay, so we wanted to kind of draw this picture and see what it looks like. So we'll use Logicsim. We'll increase magnification a little bit. So first of all, we have 2 input pins. We'll label these pins later on. And then we have 2 NAND 2 gates. So we go to gates here, and then we specify NAND. And then we make some changes first because we don't need these to be too big because we only need 2 inputs. And all the inputs are single bit inputs. So we duplicate this, we have one more. Here we go. Need to leave some space because the output of each one of these gates will go back to the other gate. So I'm going to connect these 2 pins here. And then the output of one connects to the input of the other one. So this one hooks up here, and then this one goes the other way. And then 2 output pins coming out of this one. One is here, and then the other one is down here. All right. There we go. So now we have an SR latch. And you can see how this circuit is actually symmetric. The top 2 components and the bottom the top 3 components and the bottom 3 components are symmetric. Yep.
How many data bits?
1. So all of these are bitwise connections, single bit connections. All right. So, but the interesting part about this circuit is the output of some of the components serves as the input to other components. So you can see, let me use a mouse pointer so it's actually recorded. You can see how the output of this particular gate is also serving as the input of this particular gate. But the output of this gate in return becomes the input of the gate that we started off with. So in a way, it has kind of a weird loop, okay? Because it's not the loop that you guys are used to. This one is quote unquote unstructured. So the question now is, so what is this kind of gate going to do? Well, first of all, we are already looking at the behavior of this gate for one particular case, right? Because when both inputs are zeros, the outputs are guaranteed to be ones. Why? These are NAND gates. So with a NAND gate, what happens when at least one of the input is a 0? The output is going to be a 1 because it's a negated AND, right? Because if it is just a regular AND gate, then if at least one input is a 0, then the output is going to be a 0. But because it's negating the output, so it guarantees that the output pin is going to be a 1 if at least one input is a 0. That requirement is satisfied for both gates. If you look at this gate here, one input is guaranteed a 0, so the output is guaranteed a 1. When you look at this gate, it's the same thing. One of the input is guaranteed a 0 because it connects to a input pin, so the output is guaranteed to be a 1. So this happens regardless of whether we have these interconnections from the output of gate to back to the input of the other gate. So at this point, it doesn't seem very interesting. So let's see what happens when we turn one of these pins from a 0 to a 1. And I want you guys to work with me here. Okay, what happens when I turn this one to a 1? Now it becomes kind of interesting because the moment I turn this pin from a 0 to a 1, both inputs to this particular NAND gate become 1s. What happens when both input to a NAND gate becomes 1? The output becomes a 0, right? So that means this output will become a 0. That 0 goes into here, right? And then we have 0 and 0. So that means this output would maintain the state to be a 1 because it is not bothered, should not be bothered. Is that making any sense? So let's do that. Okay. Okay, just like what we described earlier, the output of the bottom gate becomes a 0, but it doesn't bother the output of the upper gate, the top gate, because the top gate is still connected to an input pin that is a 0. So regardless of whether the feedback is a 0 or 1, the input pin being a 0 is enough to make the top NAND gate to output a 1. Okay. Yep.
Can you repeat how the wiring works?
The wiring?
Yeah.
There are no junctions here. There's no junction here. This is a flyover.
When you put an input bit, like where you put 1, what does it goes to the bottom NAND gate, and where does the other one come from?
This one
Yeah.
comes from here. So with Logic Sim, the one really cool feature is if you click on a wire, it highlights, it thickens, all of the connections, that is logically connected. So this really helps to visualize. Okay, what is this node connecting? So in electrical term, this node is connecting the output of the top NAND gate to the top output pin, but also to the input, the first input of the bottom NAND gate, which is what I was trying to use, the C, quote-unquote C code to describe. So do we have any questions at this point? Yep.
So can we not represent the whole thing as a like a Boolean logic formula?
It gets a little bit tricky. It gets a little bit tricky. But before we get to the truth table stuff, let's go ahead and let me point out why this thing is called a memory device. Because at this point, it doesn't seem like a memory device. We change the input, it changes the output. Hey, all the other gates do the same thing. The adder does the same thing. So why would this be called a memory device? What do you think happens when I click this pin? So it goes from 0 to 1. That's the question. So let's think about this. Okay, if I click on the top input pin, what is going to happen? If I click that one, it will turn the top input of the top NAND gate into a 1, right? So this pin would be turned into a 1, but would it bother anything else of this entire circuit? No. It's not going to bother anything else because this wire is still a 0, which means this NAND gate will still be outputting a 1, which will maintain this 1 here, and because this input is also a 1, this NAND gate will continue to output a 0. Okay, so let's go ahead and click this button here, click this input, and you can see how the output is not modified at all. That is the memory effect of a latch. Okay, because at this point, it's going to stay this way as long as I don't change the input pin. But then somebody's going to say, oh, okay, so that means if both inputs are 1s, then the top output pin is a 1 and the bottom output pin is going to be a 0. That is not true either. Okay, so let's see how we can change this. How do I change the top output pin to a 0? Can someone make a suggestion? Yep.
Turn them both off and then turn the top one
Do we really need to turn them both off? What is the minimum action that is needed? Turn the bottom off. Okay, because when we turn the bottom off, then the output, this one, is going to be a 1, which will turn this one into a 0. Okay, let's do that. Okay, that gets the job done. Okay, cool. But once again, people can just argue and go like, okay, you change the input and it changes the output. What is the big deal? So the magic is now what I do. If I change this 0 back to a 1, what's going to happen? The output do not get changed. Like that. So that means, even though previously we also had both inputs being 1s, but the actual state of the output of the gates has a memory effect. It remembers what it was. Is that okay? Yep, question.
Like as if,
Say that one more time.
so is it as if like the wires, the in between the second connections for the NAND gates, it's like as if they retain the memory with the help of the gate? Or?
The so-called memory has to do with the output state of the gates. Okay, let's do it one more time. Okay, let's flip the states of the output pins. In other words, let's make the bottom output pin a 0 and the top output pin to be a 1. Okay, we can do that by changing this input pin from a 1 to a 0. Okay, cool, that's done. But the magical part is when I change this pin from 0 back to 1, the output state does not change. It just maintains the output. Is that part okay? Yep.
I've heard a lot about T flip-flops previously. How does this relate to that? I know that's a little outside of
It is a smaller components compared to a flip-flop. So all flip-flops are bigger components compared to latches, and this is an SR latch. So, not sure whether I'm answering the question. I don't know exactly what a T flip-flop is. I know what a D flip-flop is, but they are all kind of related to each other. One can be used to implement the other ones. Yep.
What would happen if you press both inputs at the same time? You could do that.
Then you have a interesting situation. Logic Sim cannot do that. Okay, so in Logic Sim, even if you wire these two wires to the same, it actually does not simulate physically what's going to happen. But what you would end up with is what we call an oscillation. So an oscillation, okay, so that's a good question. But before we answer that question, what was I supposed to do earlier?
Do the opposite of what we did. We're gonna do it again.
But we did it already. Yep. Not the truth table. I remember now. Let's label these. Let's label the pins. Okay. Why is it called an SR latch? And what is the Q and NQ thing? Okay. So we'll label these things, and I'll label these correctly first. Okay. So this particular input pin is actually, it should be called /S. Not just set. It is the negative version of set. S stands for set, R stands for reset. Okay? And then the bottom one is called S/R, which is the active low version of reset. The top one here is called Q, which is basically the output. I don't know why it's called Q. That one I do not know. The bottom one is NQ, which is the negator Q. So we'll use /Q to represent it here because these are actual standard notations when people describe pins of logic circuits. Okay, so why is it called /S? It's because when that pin is negated, when /S is negated, it makes sure the Q is a 1. When /R is negated, it makes sure the Q is a 0. So one is to set the pin of Q, the other one is to reset the pin Q itself. The slash means it is active low, which means when it's a 1, it's not doing a single thing, it's not specifying anything. When it's a 0, it specifies the action it's supposed to do. Okay? So are we still doing okay so far?
You said that one more time, I didn't really hear you.
I'll say that one more time. So let's say we want to change Q from a 1 to a 0. So we want to reset that pin. Okay, because reset typically is associated to resetting to 0. So we want to reset Q. So when you look up the input pin, reset is here because it's R. But because it's a slash, it is active low, which means if you want reset the action to happen, you have to negate the pin. Instead of having a 1, a 0 means you want to do it. Okay, so let's go ahead and do it. See whether the labels are correct. It is indeed correct. And once you, so in this particular state where /s and /r are both ones, we're not specifying any action. We are basically just saying, chill. Just let it be. Idle. Don't do a single thing. Okay? If we want to change Q from 0 back to 1, we want to set the pin, which means we have to look at this pin, but because it's a slash, it's an active low signal. So that means, instead of using a 1 to specify we want to do it, we have to specify a 0 to mean that that's what we're trying to do, and that's why these pins are labeled the way they are. Q as an output, I have no idea why they use Q as the symbol for the output of a latch. Yep.
So the output of the SR latch depends on the order of the input that comes in, right?
That is, yes, it depends on the sequencing of the states of the input pins. Correct. Okay. Are there any? Yep. Go ahead.
So S dictates which is on is basically what you like. Why is it S again?
S for set.
Yeah.
And then R for reset.
So like.
And they are all with respect to Q. And /Q is just the negated version of Q. That's all it is. So in some circuits, /Q is not even an actual output pin, even though the Y is there, but it's not an output pin, which means nobody cares about the negated version of Q. Yep.
So is it if Q is off, hitting /S will set it, but if Q is on, then hitting /R will turn it off? That kind of thing?
Say that one more time.
So like if Q is 1, or sorry, if Q is 0, hitting set will turn it on, but if
you can always set it again, it just doesn't do a single thing.
yeah, and then reset turns it off.
Yes.
If it's set.
Yeah. So if something is already set, setting it one more time doesn't toggle, doesn't flip the state. It is just saying it doesn't do a single thing.
So S only does stuff if Q is off.
That is correct. So S can only change the state to 1 if it is not already a 1, but if it's already a 1, it has no effect. R can only change Q to a 0, but if it was a 0 to begin with, then it has no effect. So are we okay so far with this picture? Yep.
So because we don't really know what will happen when both are 1, like turn at the same time.
We do. we can make that kind of we can try to emulate. Okay.
Right.
Yep. So we can address that.
Okay. But what my question was is that because there's a latency issue, right? If both
Yes.
turned off or both turned on at the same time.
Yep.
We're not exactly sure without doing the physics math behind it, which one will turn on Q or not Q.
That is correct.
Okay.
That is absolutely correct.
Is that ever an issue or?
You end up with a race condition. So when you flip both pins, okay, so the question is, this state is perfectly safe, okay, because if both /S and /R are 1s, which means we're not setting, we're not resetting, we're just letting the SR latch to maintain its current state. So this is a perfectly safe state, not an issue at all with this one. This by itself is also a safe state because we are saying if Q is not set, let's set it now. If it's already set, don't do a single thing. Nothing happens. So it's a safe state. No, not a problem. This one is also a safe state because it's the opposite. It's saying if Q is not a 0, reset it now. Turn it into a 0. But if Q is already a 0, then don't do a single thing. Nothing to do. So the problem is not this state either. Okay, this state is actually okay as well. This state is, even though it doesn't make sense from the set and reset perspective, from the gate perspective, both outputs should be 1s. Okay, not a problem. So the problem is, what if we change /s and /r at the same time from 0 to 1? That becomes a problem. Because we are bypassing the intermediate state of only one of them is a 1, the other one is a 0. So what do you think will happen when we can turn both R and S to 1s at exactly the same moment? And then the propagational latency of the two gates are exactly the same. What do you think is going to happen? So let's do the mental math first, okay? So the change is initiated by the change of these two pins from 0 to 1s, right? So what is that going to do to the gates? The top gate is going to say, I'm seeing both inputs being 1s. I'm going to change my output to a 0. At exactly the same time, the bottom gate is thinking exactly the same thing. Both of my inputs are 1s, I'm turning the output to a 0, right? But because the latency of the two gates are identical, they are changing the output from 1s to 0s at exactly the same moment. What is that going to do? This 0 will go back to here, turning, let's see. This one is a 1 already. This one is going to be a 0. So the output would maintain to be a 1. No, that doesn't seem right. It would turn this one, it would turn into a 0 first. So both of these pins will turn into a 0 because of the output, but it takes time for that 0 to become effective again. So they will turn, basically it will oscillate. The Q and /Q will both become 0s, and then both become 1, 0, 1, 0 again. And the period of that oscillation is basically the latency time of the NAND2 gate times 2. Yep.
So do you mean like it oscillates, like it's just gonna go back and forth on both continually until you
Yep.
like
Yep. It doesn't lock to one particular state. It would just keep oscillating. Times 2 because the way you measure period of a wave is looking at the same transition. So you're looking at the time when it transitions from 0 to 1 to the next time it transitions from 0 to 1. So that's why you have to multiply by 2. Is that okay? But most of the time, actual physical circuits do not guarantee the same latency. So the top gate may have a slightly longer latency, and then the bottom gate may have a slightly shorter latency. Once you have a latency, and where one gate has double the latency of the other one, you don't have oscillation anymore. One side always wins. Okay? So the behavior of the circuit is no longer oscillating, and it seems to be deterministic. But it's only because of the result of a race condition. And that is what we do not like. Yep?
Okay, stupid question. Does that oscillation have anything to do with how computers keep time?
Computer keeps time using crystals, which is by design oscillating. So crystals are interesting too, because crystals are, they're not semiconductors, they're actually non-conductors. In other words, they're silicon without the doping element, they do not conduct. So the way crystals work is they translate an electrical impulse to physical motion. And then the physical motion would swing it one way, but then when it swings back the other way, it will generate a voltage. So that's how it oscillates between storing the energy as physical form and converting it back into electrical form.
So we have that. We must be able to do that on a very small scale.
Yes, well, you can only get crystals to oscillate up to a certain frequency, and beyond that, your crystals cannot do that. So we have what they call frequency multiplier. So your base frequency from a crystal is only a fraction of what you need, and then the frequency multiplier will actually multiply the frequency by a certain amount to get to the frequency that you want. So a lot of times, in processors, when you quote unquote switch the processor speed, the clock speed, you're really changing the multiplier, but not the crystal itself. The crystal is still clicking at the same frequency, but you're changing the multiplier so that the product changes. But that's kind of beyond what we are going to talk about in this class.
Sorry. Yeah.
But that's okay. You know, it's sort of related. Fun
Not
stuff.
really, but
Yep. So are we okay so far with the SR latch? Okay, it's a very funny device from our perspective because this is the first time we encounter something that can actually remember something, right? So do we have any questions about this one? Nope.
I know you said it's probably not possible on the Logism, but like, can we at least like try to make the input
Sure.
at the same time? Like maybe like make one input and then.
Yep, we can certainly try.
Does the wire link have any significance?
Nope.
on the-
Yep, it actually does detect the oscillation because it says oscillation apparent. But how it figures out, you know, there's actually an oscillation is probably just a logic, you know, just programming logic in LogicSim. So it's not really going through physical simulation. But it's kind of cool. I mean, it does detect the oscillation is apparent. Yep, it is. So are there any other questions? Oh, I can just Control Z and do that. There we go. Any other questions about the SR latch? Oh, the truth table. So the truth table of an SR latch becomes a little bit tricky. It's still complaining about oscillation because I think the only way to bring it out of an oscillation is to reset the simulation. So you can go to simulate and then you go to reset simulation and then you start simulation again and that, okay. It's enabled, stop, and then start again. So, oh, this is stepping. Enabled, re-enable it. So when you reset simulation, it also disables simulation. Let me do that one more time. Does it disable? Nope, it does not. So I guess when it detects oscillation, it automatically stops simulation, so it disables simulation. So when you reset it, it doesn't re-enable it. You have to re-enable simulation for it to go again. Okay, cool. Any other questions? So let's try to figure out the truth table. How do we write the truth table of something like this? Because it's not something that we have seen before. It's unlike all the gates that we have seen before. So let me see if I can use mouse pad and do it kind of at the bottom here. Okay. So we got /s, we got /r, we have q, and then /q. Okay. So /q is the same thing as &q in the notes, and then s and r are the same as s and r in the notes. /s is s, /r is r. Okay. So we know that we know certain things for sure. Okay. If both of these are zeros, the outputs are both ones. We know that for sure, right? That only has to do with, you know, the NAND gate only requires one input for the output, for one input to become zero for the in order for the output to become a one. Okay, so this one we know for sure, not a problem. We also know what's going to happen in this case. So in this case, we are setting, which means, you know, it is guaranteed that q is a 1, and then /q is also guaranteed to be a 0. This one, we also know for sure. It is the opposite. It is a reset configuration. So q is guaranteed to turn into a 0 if it's not already a 0. And then /q is guaranteed to be a 1 if it's not. Okay, so the only question is, what if it's 1, 1? What are we going to say in this case? Maintain state, exactly. So you be basically just, you know, specify whatever symbol you want here to say we are maintaining the state. It's not a question mark, okay? Do not use a question mark here. Because in the truth table, if you use a question mark, it means it can be a 0 or a 1, but it is not maintaining. It's just some random picking of zeros and ones. Okay? So you have to use other symbols to indicate that it's just maintaining whatever it had. Star. Yeah, I think there are specific symbols. Let me check. Let me cheat and check my own notes. Keep going. NC, no change. See, I knew I wrote that note for some reason. Mostly as note to self. So is that okay? So NC represents no change. But it doesn't apply if we are going to the 1, 1 from 0, 0 immediately. That does not apply. It has to go from one of the other 3 states. Is that okay? All right. Does everybody see at least, just kind of casually, how this is a memory device? What is the one thing that is remembering? Yep, Q maintains the state when both inputs are ones. So let me just go back to this again. So now it's remembering output is a 0. If you want to turn this into a 1, this is how you turn it into a 1, and then now it remembers. So are we good? Yep.
For /Q, you said that it's not always in some circuits?
Yeah, /Q is not always brought out to the actual peripheral of a circuitry, because a lot of times we really only care about Q.
So they just run it to ground or something if it's included?
No, it's just not connected. So /Q, if it is not needed, all you do is you just remove this part of the circuit and remove this segment. So the rest is still SR latch. It's just that we don't have the negated output anymore.
I mean, like if you were using somebody else's SR latch and they have /Q in it, but you didn't need it.
Then you just leave it unconnected. It's okay to leave an output unconnected. It's just that it's not a good idea to leave inputs unconnected. So are we okay so far? Now remember, a single NAND 2 gate is only made out of 4 transistors. 2 P transistors and 2 N transistors. So the smallest of all the memory related circuitry only needs 8 transistors. So I'm connecting this circuitry back to what we talked about in the first week. Any questions about this circuitry? The SR latch. Yep.
Why don't they use AMP gates?
Hmm?
How come they use AMP gates instead of AMP gates?
Well, it doesn't work if you use an AND gate, because you have to, the input and the output has to be related in this particular way. I'm pretty sure you can use other types of gates as a basic component of an SR latch. I'm guessing NOR can do that too, but the way the polarity of the pins will be different. Yep.
You mentioned that this is the smallest memory
Device. Mm-hmm.
Is it possible to make a smaller memory device? I mean, I guess there's no single one.
If you want to maintain a state of some kind, this may be the smallest one. It's not easy to use. It's not a very easy to use type of quote-unquote memory device, but it does, remember something. It does remember the state. All right. So are we good so far? All right. Cool. So if this one is okay, we're going to move on. And when we move on, we go to, this is a timing analysis. So we are basically saying that this is going to oscillate. So the next one is called a D flip-flop. D, by the way, stands for data. So this is a data flip-flop, and the circuitry is down here. So the circuitry down here is a little bit interesting because we are already immediately reusing an SR latch. In other words, we're just saying that, okay, let's make an SR latch. We have negation, we have N1, N2 being just regular NAND 2 gates. we got some pins. So let's go ahead and see what this circuitry would look like if we were to draw this out in Logic. I can scroll it all the way up here because the name of the device, probably will suggest what they are supposed to look like. So let's go back to here, And we're going to do the usual trick, turn this into its own component. So by clicking it, right-clicking, and go to Edit Circuit Appearance, we can now change this and label the inputs. Just to make it look a little bit nicer. There we go. And we also want to change main. I cannot remember how to change the name of the circuit. No, right click doesn't do it. Single click doesn't do it either.
Double click.
Nope.
I think you have to add another circuit.
There we go. So I have to click on something else and then click back to it. So we now change this to a SR latch. Alright, so now we can create another circuit. So we add new circuit, call this one D flip-flop. So D flip-flop, there we go. And we first find out what components we need. We need 2 NAND 2 gates, 1 SR latch, 2 input pins, 2 output pins, and a NOT gate. Okay, so we need a single SR latch. We need 2 NAND gates, which I'm going to borrow from the SR latch, like so. We also need a single NOT gate. Two input pins, and 2 output pins. This is actually how we design new products where I used to work. We just put processors, memory chips, other type of peripherals into a box, shake it a few times, and then magically, new product. Woo! Yeah.
Don't we need 2 SR in that?
Does it say 2?
S and C?
Nope, just SR. We have 2 NAND 2 gates.
Where am I looking? Oh, I was.
You're further down.
Yeah.
There are different types of D flip-flops, so you might be looking at a edge-sensitive D flip-flop. This one is not. All right, so let's go ahead and rearrange these things a little bit and figure out which one is supposed to go where. Okay, I'm pretty sure the SR latch is the output or really close to the output. How do I know that? Because we look at the output pins are Q and NQ, so we look at how the Q and the NQs are connected. Am I missing something here? Yep, I'm missing the Qs. They're not, they're never connected in here anywhere. All right. So, but the inputs are done correctly. So we'll take a look at the input. So D goes to the first NAND 2 gate, and then the SR is using the, okay, there we go. So this goes here, this goes here, and then the NOT gate N is from D, and then the output of N goes to N2. Okay, so there you go. All right, so there. Oh, by the way, there's another way to negate the input of a NAND 2 gate. If you look at the properties of a NAND 2 gate, it gives you an opportunity to negate just one of the input pins like that. So it's a cleaner representation, so I'm going to use that one. So now we're getting rid of the explicit NOT gate and use a bubble that is next to the input of a gate to negate just that input. All right, so now we'll label the input pins. Let's call this one data, and this is EN for enable. And then we just need to look at this. So D goes to one of the inputs of the top gate. EN goes to the other pin of the NAND gate. EN also goes to, D goes to the negated pin of the second NAND gate. So we got that taken care of. And then EN should go to the other input of the second NAND gate. EN goes to the, yep, there we go. All right, this is N1. Now it's time to connect everything to the SR latch. So N1.out goes to the set. And then this one goes to the reset. And then these two are just Q and NQ. So they're just connected straight here and here. So this problem, once again, is because of the, I think it has to do with the oscillation. So let's go back here. And sometimes logic sim itself, yep.
Do we have to negate the S and the R because they're not?
No. They're, in the notes, I did not use the slash, but they're actually the same label as what we use as slash here. I didn't use the slash in the notes because I can't, you don't want to name your variables with a slash in front of it. So that's why. Okay. So this is one of the things, you know, that you will encounter as well is logic sim sometimes lose, you know, just it's kind of buggy. So you have to
I've been following along and I also got the errors.
okay. So we'll restart logic sim. And now, do we still have that problem? Yep. Oh. Okay, let's click that.
Or if we like try clicking
There we go. So the enable is what allows it to change. Okay, there we go. All right. So now we have, you know, these 4 pins. Particularly, the output is not that interesting. Okay, we just have Q and not Q again, or slash Q. But the input pins are now renamed to D and EN. D is data, which specifies the bit that we want to store. EN specifies enable, which is basically saying, should we store it now? So let's go ahead and check this out, okay? If you have EN turned off, it really should not matter what you do with data because you're not enabling the device to remember the bit. Is that okay? The moment you enable the EN pin, whatever you specify as D will be remembered, okay? So let's take a look. The moment we click this pin, Q, you know, this one should become a 0. There we go. So this is called a D flip-flop, and you can see how it is slightly more user-friendly because one input pin specifies what you want to remember, the other one specifies do it now, as opposed to one pin specifies, oh, turn it into a 1, and then the other pin says, you know, turn it into a 0. Is that making any sense? Now, how does that work? How are these NAND 2 gates working together in order to make this work? When En is a 0, we want the device not to do a single thing. We want the SR latch, the underlying SR latch, not to do a single thing. But you can see how En is connected non-negated to both of these NAND gates. And because these are NAND gates, if at least one input is a 0, the output is a 1. So that means when En is a 0, the output of the two NAND gates are guaranteed to be 1s, which from the perspective of the SR latch set is saying, maintain the current state, do not do a single thing. So that's why when En is a 0, you can change D as much as you want, it doesn't do a single thing. On the other hand, what if En is a non-zero? Okay? If En is not a 0, then this pin basically goes away. The bottom pin of both NAND 2 gates basically quote-unquote disappears because it is a 1. To a NAND 2 gate, if one input is a 1, then it solely depends on the other pin to determine the output. Is that making any sense? So the moment you turn En into a 1, then D is the only pin that matters. But you can see how D is connected to the top one, non-negated, but it connects to the bottom one, negated. So that means when D connects, as far as the top NAND 2 gate is concerned, it is the same thing as a not D. But that's also what we want, because when D is a 1, we also want /S to be a 0 in order to set Q. When it connects to the bottom one, it is negated here. That makes sense too, because when D is a 0, we want this to become a 0. But that's the only way to make it a 0 is to negate this particular pin. So is that working? Just kind of intuitively. Okay. The other way you can look at En is a guard. It's basically guarding. When En is a 0, it's guarding these devices from being modified. It's guarding the SR latch itself from being modified by D. So that's the other way to look at it. So is that okay? Yep.
Can you just like activate enable and mess with it a bit?
Say that one more time.
Can you activate enable and mess with it a bit?
If I enable it right now, it's going to turn this pin to a 1 and this pin to a 0. That's the prediction. And that's exactly what it is.
So what happens when you change data? When it's
It will mirror. The moment you change D, these pins will mirror. Q will mirror D as soon as you change D, and then /Q is always the negated version of whatever you specify at D.
Okay.
Just like that.
Got it. When you turn it off, whatever state the user in stays then.
Right. Because right now En is, basically we are turning these NAND 2 gates into NOT gates, as if the second input was not there. So is that okay? So this is what we call a level sensitive D flip-flop, even though it's also just called a simple D flip-flop. It's called level sensitive because it is sensitive to whether En is currently a 1 or 0. As long as En is a 1, the output Q reflects whatever D has. So you can keep changing it. As long as En is a 1, you can keep changing D, and then the state of the SR latch will keep changing. And that's why it's called level sensitive. Now, level sensitive is kind of cool in some way. This is already better than a regular SR latch, but it also has limitations. What type of limitations do you think we encounter when we have memory devices that are just level sensitive? Why don't we want a memory device to be level sensitive? That's the other question. Yep.
It can only remember the very last thing that it did.
It can only remember the last state before enable turns into a 0 again. Yep. So, but why would that be a problem? Your analysis is correct, but let me push that question one step further and ask why would that in return be a problem? Yep.
When we turn off the computer, all of them go off.
Okay, that's an interesting question. Okay, what happens when you first turn on a computer and what happens when you turn off a computer? Those are very good questions. But the reason why we do not like level sensitivity is not because of that. Anyone else? Oh, come on. Yep.
If the last configuration was faulty, then you would be stuck with that.
That's true. Okay, so in a computer, okay, so let me give you the bigger picture. Okay, in a computer there are many devices, right? So the result of one device serves as the input of another device and so on. Now we have seen something like that already. We have seen something like that with an adder or subtractor, where you have multiple stages of gates and then the output is not valid until the previous stage is correct and so on and so forth, right? It's staged. It's staged, but it's not clocked. In other words, you present the input and then you just wait X amount of time, the output is going to be correct, okay? But that can only be done to simpler problems. To more complicated problems, it doesn't work. For instance, if I want to increment a variable like 3 times, that circuitry doesn't work. It cannot keep track of steps. Is that okay? So in computers or in a processor, many times we have to quote unquote keep track of states. And why do you think level sensitivity is not good for that sort of thing?
Is it just that it forgets everything after you hit the EM, like you can't remember anything past one state?
It cannot, there's no control over the moment this thing is going to update. That is the problem. Okay, let me draw a picture. Okay, so it will take a little bit of time, but it's worth it. So let me just say that one more time as we wait for this setup to work. The problem with level sensitivity has to do with the window of update is too long. We are not limiting to a single moment and say, now go update. Yep. As long as EN is a 1, whatever the input D is will change the state of Q. So from that perspective, the level sensitivity applies to the EN pin itself.
You're saying level sensitivity is that EN will change it?
Level sensitivity applies to. All right, it doesn't like it because I was too slow. Let me do it one more time. Okay. It's lost its state already. Okay. See if I can do one more time. There we go. Okay. There we go. Okay. So level sensitivity has to do with this. So we want to track down 3 signals. The first one we want to track down is EN. The second one we want to track down is D. The last one we will track down is Q. Okay. So level sensitivity means if EN is 0, then you can do whatever you want to do with Q, and nothing happens to Q. And you can do whatever you want with D, but nothing happens to Q. So if Q is already a 1 or 0, it maintains its state. So let's say Q was a 0 to begin with. It doesn't change at all. Is that okay? But the moment you change EN from a 0 to a 1, the moment you change from a 0 to a 1 with EN, if D keeps flipping and flopping like this one, D will mirror, Q is going to mirror. So Q is now sensitive to all the changes. That's why it is called level sensitive. because as long as En is at a particular level, the device will behave in a certain way. So why is this not desirable? That is the question. Because if this is okay, then we don't have to create more complicated circuits that are called clocked D flip-flops. Yep.
Is it like the edge that it corresponds to when En changes? Like, is it like a rising edge, leading edge kind of thing?
It has to do with how do we do timing. How do we do a relay thing, right? So I got something computed, I need to hand it to you so that you can use it as an input. But how do you know when is a good time to sample the line and say, oh, okay, tech is ready at this point. Let me sample right now, and whatever is presented to me at this moment, I'm gonna remember it. Yep.
So it's difficult to pinpoint specific point in time at a specific state.
Yep.
To where D is at, because you're turning it on and off without any correlation to the timing of it. Is that correct or no?
Yep.
Okay.
It basically, if we can only do level sensitivity, then we cannot implement things that are quote unquote clocked.
Okay.
Where things have the lock step.
Mm-hmm.
So this is the previous step, and the next step is this one. The next step is this one.
Mm-hmm.
But the output, in order for you to sample and know when to sample, the timing has to be right, because everything is working, everything is changed. You cannot have a whole change. Okay, let me this. I think this will help. Okay, so let's say you have this device, and this device, and they have a dependency like this. Okay, so when you have devices that are clocked, that means at a single the input changes and then the output changes over here. The input changes here and then the output changes here. The input changes here. The output changes over here. If you have a circuitry that is level sensitive, then we don't know what is a good time to sample and do the computation. Yep.
So you're saying Q would be slightly behind the change of D?
We want to turn this into a way so that when this guy is computing and not ready to output, we don't want this one to use the intermediate incorrect signal to do whatever this guy needs to do. So we want to tell this guy, don't rely on this line here. Don't even try to interpret or read or remember anything, because during this time, the early device is still computing. So we want to define an exact moment, just one single moment, where we can say, now it's ready. Okay, take whatever the first device is outputting as if it is your input. Now is a good time to sample it. So we don't want that amount of time to be wide like this. We want it to be a single moment.
So almost like a flag kind of. Is that right? Or no?
You're looking at a transition.
Okay.
The other way to think of it is flash photography. Okay, blurring motion, stuff like that. When you look at the cursor flying over, we see something that's moving linearly. I know it's kind of already quantized, but for the most part, we see it as a single line. But if you're using flash photography, a single flash, it will quote unquote freeze the pointer to a certain location. You're not going to see the continuous motion. You only see the cursor at a single point. We want that effect. Is that okay? All right. So we will definitely see the processor, or situations where that is needed. And we are running out of time today. We got about 3 or 4 minutes left. So the next one in section 5 is exactly the cure to that problem. It is called an edge-sensitive D flip-flop. And the circuitry is a little bit more complicated, and the analysis is even more complicated. So I definitely don't have enough time to analyze or even to present the circuit. But you can go ahead and try to draw the circuit out in Logic first. And this is kind of a combination. And you can see how it's actually making use of 3 SR latches and 2 AND gates on top in order to implement this particular circuit. So in this circuit, we have clock, EN, and data. Clock is edge, is basically what is providing the edge. EN is saying, okay, should we pay attention? And then data is what we are trying to remember. Okay. In previous semesters, I have analogies that would not be politically correct today, so I cannot use those analogies. But they're really, really good analogies if you understand the stuff that is not politically incorrect. So I cannot use those analogies anymore. So all I can say is, in this case, if EN is a 0, it doesn't matter what the other pin is saying. Okay, if EN is 0, the device is basically off. It is not paying attention at all. When EN is a 1, okay, then we still need to wait for CLK clock to have a rising edge. And right at that moment, okay, when clock is turning from 0 to 1, this device will sample data and say, whatever data has now, I'm remembering it. But right after the edge goes away, when clock becomes 1, as a stable signal, you can change data whatever you want. You can change data again to whatever you want, and the device does not pay attention anymore. Yep.
So is it kind of like in the D flip-flop, kind of breaking that up into like a double key lock where you have to have clock and EN to pay attention to the data?
It's kind of like one thing is, I really hate when I cannot use the politically incorrect example because it is so relevant to this discussion.
Can you just use it?
No, I would rather not because it might, upset some people. Huh? I have to think of other devices that has a similar nature.
You can like change a couple letters.
Rhymes with.
Use animals.
Now, animals don't have edge sensitivity. Well, I think photography is a good way to do it. Okay, think of it this way. Okay, so this is a good way because I know no one's going to be upset when I talk about photography. Okay. Okay, so think of it like this. You have with most cameras you have a shutter release. Okay, so shutter release. Shutter release is controlling the moment. Okay, and then you have background lighting. Okay, so you have lighting, and then you have the film or sensor. There we go. Okay, so this is a good one. This is really good. So if you want to capture something on film or with a digital sensor, you need to have light to be on the subject. Okay, whatever you're taking a picture of, if that thing cannot emit light itself, you need to turn on the lighting, right? You need to shine some light on whatever you're trying to take a picture of. So lighting is kind of like EN. Okay, you can turn on the lights in a whole room and nothing happens, right? But shutter release is your clock, CLK, because the shutter, when you press the shutter release on a mechanical camera, the shutter only opens for a very brief amount of time, and only that within that very short amount of time, you're going to capture whatever the light is shining on, and then right after that, you can continue to have light in the room, but the sensor or the film is no longer recording anymore. So it's kind of like that. So in this case, the timing is controlled by CLK, but whether you can take a picture of something that's usable is controlled by EN. Yep.
The film is Q.
Hmm?
The film is Q.
Sort of.
And then the world between.
Whatever you're taking a picture of is D.
Yeah.
So you're basically controlling at what moment am I going to capture something. Is that okay? So with this analogy, there's one more thing that I need to point out. is the shutter release refers to the button on the camera when you have an older camera. So when the shutter release is not pressed, it doesn't do a single thing, right? It is when it is at the moment that you actually press the button that the shutter release mechanism goes like that, right? But after that moment, if you keep pressing the shutter release button, it doesn't do a single thing either. Now that only works with old mechanical cameras, because these days you guys do not actually have mechanical cameras anymore. When you keep pressing the shutter release button, it just keeps taking more shots. That is not what I'm trying to illustrate here. But is that okay? So the shutter release, the moment you press the button, you press the shutter release beyond a certain point, that's the moment you capture the picture. Is that okay? Yep.
I know that you mentioned that you can press the shutter multiple times before posting. Is this how then do you keep track of future data changes? So like
you have to reset. In other words, you have to after you press the shutter release, you have to release it and then press again.
Okay, so it can't just.
So you cannot just keep pressing it and expect it to take more pictures. Once you press the button, you have to release the button first. In other words, the moment that it's going to capture the image is when when the button goes from here to here. But once it crosses that threshold and has taken the picture, you can keep pressing it in that state and nothing is going to happen. Okay. Okay, so next class is going to be our exam. So we'll continue this discussion on next Tuesday after we talk about the exam questions. Huh? We're doing the exam here. So the entire class, both lab sections, we have the exam at the same time.
And will we be doing anything for that?
We might be doing something for lab, but it's not going to be related to the exam. Because otherwise, the early lab is going to have the equivocal advantage.
Yeah.